The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.
Benjamin J. Heckendorn was a mild-mannered graphic artist until he was bitten by the electronics bug. Now, every week he takes on new projects, shares tips and tricks, and answers your viewer questions on The Ben Heck Show.
Hello and welcome back to the Ben Heck Show. I've used this custom-built AVR development board in past episodes, and we've had several people ask about it. So today I'm going to show you how to put together one of your own and point you in the right direction of the schematics and diagrams you'll need online. Let's get started. But first, the news. Today in Ben News, I'd like to show you this new 3D printed elevator I made for my Ghost Squad pinball machine. The ball comes in here, rolls down, and then the elevator can come down like this and make the ball go into a secret path. 3D printing was great. I was able to 3D print a rack and pinion, sidewalls for the elevator, and even these main supports. So yeah, it's great. It's quite strong and it's three-dimensional, so this is a great example of what you can do with 3D printing. It takes a while to print all this, but it's worth it. Let's start by talking about the differences between an in-circuit serial programmer, or ICSP, and a serial bootloader. The in-circuit serial programmer usually requires you to have a little box, the programmer. This box connects to your computer via a USB cable, and then it connects to your development circuit or microcontroller via a 6-pin programmer. Now these boxes vary depending on what kind of chip you're using. There's a certain one for an AVR and a different one for a PIC, but they basically do the same thing. And they're typically used with a program on your computer such as AVR Studio 6 or a standalone program that flashes hex files. This is the method typically used for professional development and also flashing bootloaders. Now let's talk about a serial bootloader, which is what the Arduino uses. You need to flash your microcontroller with a bootloader program which sits at the beginning of memory. You need to flash the chip using your in-circuit serial programmer. But once you do, you're able to program the chip using the RX and TX serial communication pins. However, you need some sort of interpreter between that, so you usually have a USB to serial adapter, typically an FTDI chip or another small microcontroller, that takes your USB commands, translates it to the old school RX TX, and then your chip programs itself from there. So if you want to flash your own chips for development, you should definitely get an in-circuit serial programmer. But then you can do it this way, which is a little easier. Knowing that, let's talk about what we're going to build in this episode. We're going to take a little PCB and put a microcontroller socket here. We're going to use the ATmega 328 and also a smaller socket here for the ATtiny, so you can program either of them. There'll be a 6-pin in-circuit serial programming header here, which works with the AVR programmer. We'll have a crystal on board for driving the larger microcontroller, be a power switch, DC jack, and plenty of pins so you can pin out what you're doing. So you can use this to flash the chips, but then you can just pull the chips out and put them in another solution. Here are most of the parts we need. Here are the microcontrollers, sockets, switch, power jack and plug, capacitor, indicator light, crystal, and a header. And we also have these headers here, female headers, for adding other things to it. So let's get started. This is important. I got this off the Arduino site. It's a schematic for the Arduino Uno. Now, this is the part we actually need to worry about. This is the microcontroller, and we can use the same pin out for the larger chip and the ATtiny. And this part of it right here, that's the in-circuit serial programmer. So that's how it's going to be connected on our board. So this is the most important thing right here we need to copy. I added a little header here so the crystal can be removable. These microcontrollers have internal crystals, but if you want an external crystal, I want the option to be there. I've started with the header here. This is the pins 28 down through 23, and these are the analog connections, as you can see in the schematic. So I just simply use little bits of wire to jump it over. Just manual soldering, fun. I do it all the time. Reset button with a pull-up resistor. The pull-up resistor will put positive voltage here on the reset line. When you push the button, it pulls the reset line low, resetting it. And I'm going to tie the reset lines of both processors to the same pin, because you're not going to use both of them at the same time, one or the other. So I'll attach this one here, and then we'll have both of the resets hooked up. Here I have common ground lines wired in. See how we go to the reset switch, the tiny, and the AT Mega. There's also a positive voltage rail here. And positive and negative voltage also goes to the header jack that we're going to use for programming. This is the jack that you plug your AVR ISP programmer into to program the device. So as I continue to wire it, I'm going to hook up the SPI bus from the programming header to both of the chips. The SPI bus, or serial peripheral interchange, or interface, sometimes it's called, is how the chips are actually programmed. Here's how the programming header was wired. We see on the schematic that the pins go to the 3 programming pins on the AT Mega, which is 17 through 19. We've got that hooked up here with these jumpers. Then in the AT Tiny, we're using pins 5 through 7 here. And you can see those have been connected to the programming header as well. The programming header also needs positive 5 volts, and that's as a reference, ground, and the reset line. So our reset button is also hooked up to the programming header. That allows the programming header to reset the processor and get it ready for programming. Now here's the power portion of it. We have a DC jack coming in, capacitor to smooth it out, on and off switch, an LED indicator, and then the power goes to both of the microcontrollers and the ground goes to ground. So we'll just hook it up here, click it on and test the power, make sure the power is going where it needs to go. Yep, 5 volts there, and then in this one it's 1, 2, 3, 4, 5, 6, 7. Yep. So that's pretty much all the wiring. I'm going to label these pins, and now we can move on to the actual programming part of this.
Pitching your big idea to senior management? Easier said than done. Researching, designing, and prototyping your big idea using the Node on Element 14? Yep, much easier. Discover how we're listening to your feedback and building a better experience.
Now it's time to program. Here are the parts we need. There's a power cable to plug into our board. Even though this header has a power connection on it, you can't actually power this board through the programmer. You need its own power supply. Then of course we plug in our programmer right here. Then we plug the programmer into the computer via the USB port. The first chip we're going to program is an AT Tiny 45. It's a small 8-pin AVR microcontroller. Let's turn on the power. Light turns green. Okay. So this is AVR Studio 6. You can download this development environment for free from the Atmel website. We go up to Tools and Device Programming. Then we wait a few years for it to load up. Okay, we select our tool. We want the AVR ISP Mark II. Device we have to set to AT Tiny 45. There it is. Interface ISP, that's correct. We hit apply and see if we get anything. Okay, that worked. So we hit read the device signature. All right, so we got a result there, which means that we are connected to it properly. Let's see, this ISP clock, we can just leave that as is. The ISP clock it actually sets the speed at which it gets programmed rather than the speed at which it runs. You always want the clock to be slower than its drive speed so you don't break the chip basically. So you can always program it at its slowest speed and at least get in there and change stuff. So now that we know that it's connected, let's write a little sample code to test out our AT Tiny. So I'm just going to hook up this LED to PB0 of the AT Tiny. So ATtiny has voltage, ground, and then it has 6 I/O, although one of them is also used for the reset line. So I typically leave that one alone, because if you try to use it as a digital I/O, you'll need a high voltage programmer. So basically we have PB0, PB1, PB2, 3, and 4. And 3 and 4 also can be used as analog digital converters. The first 3 pins here are also your serial clock, master in, slave out, master out, slave in for your programming. So when you program the ATtiny, you don't want to have things like a LED connected to it, just so it won't interfere with your programming. I mean, it doesn't always interfere, but it might. All right, so in AVR Studio, we go to New Project, we make a location for it, and we select GCCC Executable Project. Okay. All right, now we select our device, which is going to be the ATtiny, specifically the, oh, come on, don't do that. We select our device, which is going to be the ATtiny 45. Here we have our pin direction, data direction, port B. I'm ORing a 1 into the 0 position, which makes it an output. So now we need to do this. Port B, OR equals, that same thing, 1 shifted 0 to the left. Then we do a delay microseconds. And the nice thing about something like, AVR Studio is it's based off, what's that thing Microsoft has? It's based off Visual Studio, so all the keyboard functions and tricks that you have are all there, including autocomplete. Now we're going to do port B and equals the invert of that, which will turn off the bit, and then another delay microseconds, 1000. All right, now we're going to hit F5 to debug and compile, and that will also send it to our chip that we previously had connected. There we go, a blinking light. Here's something else we should look at. I'm going to go to device programming again, read the chip, and go down to fuses. Fuses are what sets certain things on the chip. So here we're using the internal clock, but by default, clock divided by 8 is on, which means our 8 megahertz clock becomes a 1 megahertz clock. If we want to use the full speed of the internal clock, we turn off clock divided by 8 and hit program. So now we're running 8 times faster, the full speed of the internal crystal. But now we have to change our programs so we have the timing right here. Up here, before delay, we put define frequency CPU 8000 UL. So basically we're saying the frequency of the CPU is 8000. That way our program knows how to calculate the delay function. If we put that definition after delay or didn't include it, it wouldn't know what speed it is, and therefore it wouldn't be the right rate. So if I program it now, it knows what the proper speed is and frequency, and the LED is back to flashing once per second. Now that we've used this board to program an ATtiny, let's use it to clone an Arduino. All right, so we have an Arduino, we give it power, and then we also plug in the programming header. That's what these extra headers are for on the Arduino. Now in AVR Studio, we go up here and we change our device to ATmega 328. Somewhere here, ATmega 328P. Okay, there we go. Hit apply, we read it. Okay, there's our device. We're going to go to memories, and then what we're going to do is we're going to read the memory off of the Arduino. So I'll just put it on the desktop here. Just call it Arduino BL for bootloader. Okay, now it's copying what's on the Arduino and creating a hex file. You can actually set bits in your chip to keep it from being copied, to kind of protect it so no one can take your code. Obviously they don't bother doing that with the Arduino, but in professional applications they might actually do that to prevent people from copying. It's basically a one-way street. You can't read anything on the chip ever again. Okay, now we're going to unplug this. So put this aside. Move our AT Tiny. Yes, I know a toothpick isn't really the proper way to do this. You'll have that. Wow, I'm doing all sorts of crap today. You know. All right, put in 18 mega 328. All right, put our programmer on this. Plug it in here, turn on the power. We have it plugged in, so I'm going to go into AVR programming and read it. Okay, I've got an error. Oh, we need the crystal. Without the crystal, it won't work. This thing has an internal oscillator as well, but if its fuses aren't set to use the internal oscillator, it needs an external oscillator. Turn it back on. Okay, we go here, we read it. Okay, we have a device signature, which means we're good. So we do a couple things. We go into memory, and we load up the Arduino BL file we just got. Now we program that to this chip. Doop, 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 doop. This takes a couple seconds. Oh, it's done, okay. You have to do a few more things. We go into fuses. You have to set them a certain way. SPI enable, you definitely want that, because if you can't program it via SPI, then you can't. You basically need a high voltage programmer, but that's what we're doing. Boot size, this is actually how much room the bootloader takes up. And then boot on reset, clock divide, and then, oh, here you can see the external oscillator right there. So, actually, yes, okay, so that's what we want. All right, so we program those fuses in. We also program the lock bits, basically no lock. All right, so now we've basically cloned in Arduino. Now we can try to hook it up using the serial bootloader we talked about earlier in the episode. So this FTDI chip, the main connections we need from it are CTS, RxTX, DTR, and ground. DTR, which resets it, goes through a capacitor and then to the reset pin of the MCU. Then we have RxTX, which go to the RxTX pins of the MCU. And then finally, CTS, clear to send, we just put that to ground. So this here is a little module that simulates what this does. This is a module that does the same as this. It does your USB to serial conversion. So when we go into the Arduino program, we should be able to send it. And there we go. The classic Blink program is working. So we flashed our own chip, and then we made our own circuit to bootload it. So we built our own development board, flashed our own hex file for the bootloader on the Arduino, and then we used an external serial to USB programmer to program it. See, in this case, there's a lot of stuff in here that you don't necessarily need, like the USB to serial converter, the big USB jack, some of this power stuff. By having the USB to serial programmer be an external part, we can remove it after we're done, so we can embed the chip. I mean, this converter chip actually costs more than the microcontroller itself, so, you know, we kind of made it minimalized. So we can actually unplug this and it will keep running. Blah. Because the chip has now been programmed. Of course, if you remove the crystal, it won't work. Put it back in. Yay! So there you have it. We built our own little AVR development board that works with both AVR Studio and Arduino. For more information, check the links below and do Google searches to find the schematics you'll need to wire up a board of your own. It's quite simple. Today I'd like to rave about Kickstarter. It's really exploded this year with several projects making multiple millions of dollars. It helps small businesses and entrepreneurs get their dreams off the ground, and larger companies, especially in gaming, to make the kind of things publishers never support anymore, despite there being an audience for it. I do have some rants though. The new Kickstarter guidelines impede electronic projects. Success stories like Ouya and Digispark would be in violation now. There's also a lot of failures and missed deadlines on the site. If you're kickstarting something, take your money and time estimates and multiply them by 2.6 to cover mistakes and delays. Then add 10% for Kickstarter and Amazon payment fees, as well as 30% for Uncle Sam. Also keep in mind that shipping is expensive and time consuming. Packaging alone can really add up, so make sure the rewards are worth the shipping. For example, don't spend $5 shipping a $7 t-shirt for a $20 pledge. Today's question comes from Brendan, who asks, is there a type of legal documentation I can give to potential designers to help me work on my idea, yet protect my idea as well? For legal advice, you should always ask a lawyer first, but in my experience, I often have to sign an NDA, non-disclosure agreement. Basically, this prevents me as a designer from sharing or even talking about what I'm working on with a third party. You should also draft a contract which ensures your vendor completes their work and sets a pay schedule. Should something go wrong, these documents will provide a legal recourse for protecting your interests. That's all the time we have for today. In our next episode, I'm going to be building some custom computers for AMD using their new Trinity line of APUs, along with the new micro ATX boards from MSI. We'll see you then. Stay tuned at element14.com/TBHS, where you can join the discussion, suggest builds for the show, and even have a chance to win upcoming builds. Remember, you can always email build ideas to benheck@element14.com. Thanks for watching.